Okay, I think we can start now. Hello again, it's me again, Rommel. We'll continue the third lecture on this SIMPA course on an introduction to inverse problems, and just get the chalk. Okay, and so in this lecture, I'll proceed to another fundamental regularization method in inverse problems. So in the first two lectures, we talked about Tikhonov regularization, which is a very well-studied method for solving inverse problems, and we focused on its convergence in terms of the discrepancy principle. And as we saw, the discrepancy principle requires two things: the information about the noisy data and the noise level. And we established the convergence of the method and at the same time the convergence rates. And let me just go back to that last result about the convergence rate. Now, to emphasize this one, I would also want to emphasize that here the convergence rate is something, I mean, if you look at this bound over here, this tells us that as long as we satisfy the source condition, we can see that the error is of this magnitude over here. And for Tikhonov regularization, the nu there is a smoothing parameter. And what this tells us is also detailed in the lecture that I put in the lecture notes by, that reference by Engel, Hanke, and Neubauer. This error bound here, which is related to the convergence rate, is a sharp error bound. And you notice that as our smoothing parameter nu increases, notice that our error here approaches something like delta raised to 1. So that means as the smoothing increases, the ill-posedness of our problem becomes severe, which leads us to this larger error. Okay? And also, for instance, if I have, let's say, eta equals 1, then you'll have an error big of delta raised to the 2/3. Okay, and for that one, we can also relate this method, this convergence analysis here, to another type of regularization method. So regularization methods are like in two camps. One are those variational methods, like the Tikhonov regularization methods. Another one are iterative methods, and the simplest iterative method in regularization is the Landweber method. There are also methods that are in between that behave like an iterative scheme, but at the same time they have some variational computation into them, but we will not tackle them. We'll focus on the Landweber iteration, which is also very well studied. So if you have a linear inverse problem, it's as usual, in terms of an operator equation, Ax equals y with the noisy data y delta. And suppose it can be solved formally by minimizing this least squares functional, as you can see here. Okay. Now, if you observe that the gradient of this function is given by this one, a star times x minus y delta, And by applying a gradient method to minimizing this least squares function, this leads us to this iterative equation where you have the latest iteration equals the previous estimate updated by this multiple of the gradient step at the current solution x sub n. Here we set the initial guess x sub O to be equal to 0, and this makes the analysis of the method simple, and some number eta greater than 0. And notice this eta here controls controls how far do you take from the gradient step. In some iterative regularization methods, the step size, in this case that's eta, this is being updated at every iteration, it changes. But here in this course, for simplicity, we'll consider a constant eta. So a constant step size every iteration, just to simplify the analysis. And this method is called the Landweber iteration. This was formulated by Louis Landweber back in, if I'm not mistaken, around 1950s. And to illustrate this method numerically, here are some numerical examples. And as also as you can see, it's easy to implement this numerical scheme if you have the operator A in our discretization. That means you have a matrix A, and then you have the noisy data y delta, and so it's easy to implement this one. And also you notice that in this example, same as in the previous examples that we used for Tikhonov regularization, notice that when we run the iteration by different number of iterations, we have different approximations. But as you can see here, as our number of iterations increases, let's say it's like this, in the example from left to right, from 100 to 500. Notice from increasing the number of iterations from 100 to 500, notice the approximation gets better. It's also the same when we increase it out further up to 4,000 iterations. But notice when we increase further up to, that's 80,000 up to something like 500,000 iteration, notice that our solution gets worse. It starts to oscillate very badly. And this indicates that for this iterative regularization method, we need to terminate it at some number of steps in order to reconstruct the solution. So if we devise a rule that we stop the iteration here, when we satisfy this one, then we take the approximate at that iterate as our final approximate solution. We will discuss that later on. So same in Tikhonov regularization, we need to fine-tune the regularization parameter. In this case, the number of iterations play the role of the regularization parameter. Okay, and then that's what we will focus at least on the next 4 hours of the lecture. We'll devote it on this iterative method, and maybe if we have time, we'll focus on generalization of this iterative method. So how does it work? So in order to, same as in the Tikhonov regularization, we need to analyze the convergence of the method. First, we start on the convergence of the Landweber method on the noise-free case. So first we consider the convergence property of the sequence of iterates from the Landweber iteration when we have unexact data instead. And that leads us to this helpful lemma over here. This tells us that for step size large enough, and that is emphasized by this one here. Okay, so let's say if eta is between 0 and some multiple of 1 over the square of the norm of our matrix, then the residuals for every our residuals increases rather decreases. Okay, and if you look at that a condition there. Okay, this tells us that if you're going to choose the same step size at every iteration, then our step size must be large enough so that it does not exceed this number here, which, as you can see, is in terms of the square of the norm of A. And the norm of A, of the linear operator A, is related to the ill-posedness of the method. And what this tells us is that if your problem is more ill-posed, then the norm of this matrix blows up, and that forces you to choose a step size that is small. Okay. So to analyze this one, it uses the same tools as we have last time, but it's a bit different because we only focus on the iterative scheme over here. So from the definition, in order to analyze this one, first let's write the let's write the method without the noise. Okay, and then let's use this very useful decomposition of the exact residual at ax n plus ax sub n plus or minus y. So let's first write it in this way. It's a x sub n plus 1, a sub xn plus axn minus y. So we group the terms like that because that's how we will analyze the error. So by taking the inner products on both sides, we will get the following. So that will be square, and that will be equal to this one. Square plus the square of the norm of the second group there, and then plus 2 times the inner product of these two terms here. And then by grouping the terms, we will get that first equation over here. So that axn plus 1 minus a sub xn, if we just write that one. And that will be equal to this one. But not in the equation there. In this equation here, we can write it as a times xn plus 1 minus xn square plus that inner product over there. And we can also group it in this way. Okay, and then at this point, we can apply the definition of the iterative scheme here. So we can just simply write again in that manner. So that will be equal to that one over there. So that's eta. So let me just write it, because we will need it later on. So that's A times A. So here we can substitute this one here. So you can just solve for xn plus 1 minus x sub n, then use this one and then square it. So we have something like A times A star times axn minus y. Okay. And the same thing here, but we have minus eta there, so we can put the minus here and then put the eta here, and then we get something like this one. And also we have something like A times A star times but notice because A is bounded, so it has an adjoint, so we can put this little a here to the other side and make it adjoint, and then you have this one. Okay? And then after that, we'll get this term over here, and then we can rewrite this further in this way. But first, let's apply an inequality here related to norm, so that will be equal to less than equal to eta squared times norm of a squared times norm of what's left inside square minus 2 eta times this one here. We can write by inner products, we can write it as the square of the norm of that vector over there. Okay, and then we can rewrite this one in this manner, so we can factor. Yeah, notice they have a common factor there, so we can put it out. So we're left with eta times eta norm of a square minus 2 times the norm of a star times axn minus that one. And then this proves the result, because from our condition on our regularization parameter, this means that eta times norm of a square minus 2 must be negative. So this term here is negative. It's all, the rest are positive, so this is less than equal to 0. And we finish the proof. Okay. So what this tells, what this result tells us is that when we run the Landweber iteration with an exact data, we should expect that the residuals to decay, as long as we have step size chosen appropriately. Now, we can also say the same thing with the errors itself. And here is another useful lemma here. So again, as usual, we assume that our step size eta is chosen appropriately, and let C sub O be equal to this term over here. Then the approximation errors should decrease on when we have exact data, and at the same time we have this series of the residual terms to be taken to infinity to be bounded. What this result tells us is that when we run the Landweber iteration method with an exact data, then we should expect that this one the sequence of residuals must converge to 0. The proof is very similar to the previous lemma that we proved. Oops. And how to prove it? It's almost like this one. So I'll just I'll try to sketch the proof over here. So example here, by using the same decomposition as what we did for the errors. it went way further down. Ah. Yep, that's enough. Okay, stay there. Okay. So I have this one here. So it's the same procedure as this one, as you can see. So the proof of the monotonicity can be proved on the same technique as in the previous lemma. Now, I want to focus on proving the second part of this lemma. So that's the first result. Now, if you look at in the monotonicity result, in particular in the last inequality here, okay, there, by taking that last inequality there, we can rewrite it further that if you have C sub O times the norm of xn minus y squared less than equal to this one. Okay. And then suppose we sum it up from, let's say, from j equals 0 to n. So we'll just update the subscripts there. Then, and by doing the same in the left-hand side, then what you will get some telescoping series or telescoping sum over there. So that will be less than equal to the first term here at x sub O minus x daga minus, and the last term will be somewhere like also this one. Okay, just to avoid confusing you guys, I'll just make it dry. Okay. And then this left-hand side is bounded above by a simpler bound. And we can further bound this one further by a fixed bound, which is this one. So it's a finite, and that gives us the second result. Okay. So we have proven some. So we've proven some necessary lemma to prove the next theorem, which simply tells us that for a step size chosen appropriately, then the sequence of iterates by Landweber method converge to the minimum norm solution. And to prove that it follows a fundamental proof that we do in optimization theory. If you've taken some optimization course, you've probably done this proof, but it's just done slightly different. So here's how it works. First, the first thing that we do is first we prove that the sequence of approximations on the exact case is a Cauchy sequence. And then we'll use again the same error decomposition as in the last one. Okay, so let me just write that one again. So that's like a okay. So yeah, that's x sub n square minus xm square, then minus 2 times this one. Okay, and now, so what we want to do here is we'll analyze these two terms here. In fact, we can to prove this using this one, we'll use the previous lemmas that we have. But first, let's focus on this one, this inner product over here. And to analyze that inner product requires us to find the definition of x sub n And what we will do is this. So it's like this for n from 0 to m minus 1. So we let it less than m. So we take the absolute value of that one. So that's a note we can write this difference here as sum of the difference of the successive iterates of the Landweber iteration. So from this one, so that will be equal to, actually we can also change, it's safe to change the indices here. Let me just rewrite that one. After all, we're taking the absolute value, so that's fine. Be careful of the signs. So what you have here is that we can write x sub m as x sub n in this manner. So that's x sub m minus 1 plus up to x sub n plus 1 minus x sub n. Okay? Because here you have something like x sub m minus 1 minus x sub m minus 2. It's cancelled, so you're left with this one. In the end, this will get cancelled. So from here, we can substitute this term here as a sum, and then by, of course, inner products, we can write it further in this way. And that's from j equals n to m minus 1. And that's how we get the first term over there. And then by applying the definition of the Landweber iteration, as what we've seen earlier, and then by taking a Cauchy-Schwarz later, but before that, let's just do it step by step. So this will be equal to, but now it's safe to do the, it's safe to apply triangle inequality now. So this will be less than equal to the summation of, that's a star minus y, and then you have this one. And then from this one, we can move the a star on the other side, so that will be equal to this one. Minus y times a, then multiplying a directly here, because that will be just equal to a times xm minus x dagger. And then multiplying a on those two, on both terms, that will be axm minus y. Because not ax dagger is y. Okay, then that's from then by Cauchy-Schwarz, then we can bound this further by this one. Okay. Now, if you look at the second term there, note from lemma 3.16, it tells us that if you look at this residual at the mth iteration, then we know that the residual at that iteration is less than equal to the residual on the previous iteration. In fact, it's less than, and furthermore, it's also less, and this one is also less than equal to the residual in the previous iterate, and so on. And then this, in general, it's also less than up to the ax, the residual at the nth iterate, which is where we start here. here actually in the sum. So what this tells us is that this mth residual is bounded, rather is less than equal the residuals from the iteration j, where j is less than equal to m. That means that this one can be bounded above by the jth residual, where j runs through this summation here. So we'll be left with something like this. Much simpler bound. Okay, and then we have that much simpler bound over here, okay, which is actually also in the slides. Okay, so you have that simpler bound over there. Okay, now, oops. Now by rewriting this one with that bound over there, then we can actually bound it by, oops. We can apply a triangle inequality there again, so we'll have something like this one. So we will be left with something like the norm of x sub n squared to be less than or equal to, where was I again? Yeah, somewhere there. Then because that's minus, so we can bound above that -2 times the inner product in this way, so that will be equal to plus the summation of that summation over there that we just derived. Now we'll use this argument over here. Note that from the previous lemma, what was that lemma again? 3.17. By lemma 3.17, we know this one, in fact, each term here must go to 0, so therefore this goes to 0 as let's say m goes to infinity. Okay. Also as n goes to infinity as well. Okay. Now if you look at the first and second terms here, you can also argue that the sequence is convergent. In fact, we can use calculus here because from lemma 3.17, we know that this is monotonically decreasing, and also it's also bounded. Because it's bounded below by 0, and also it's bounded above. But you can have an upper bound here, which is something like this. Okay. So it's bounded, it's monotonically decreasing, so therefore it's also convergent. That means and because it's convergent, the limit must be unique, so that means this one converges to some limit, let's say e, and also this one also converges to the same limit e. So that means as m goes and n, or as m and n go to infinity, the right-hand side, the entire right-hand side goes to 0, and that means that the term on the left-hand side goes to 0, okay? As n and m go to infinity. Now, what this tells us is that the sequence of iterates is a Cauchy sequence. So therefore, we have a limit x star. So therefore, the sequence converges to some limit. Let's say that's x star. N goes to infinity. Okay. Now let's argue that this x star is indeed the minimum norm solution, and we can follow this argument right here. Note from the previous lemma 3.17. Note this by lemma 3.17. This also implies that AXN, okay, minus y goes to 0 as n go to in infinity, okay, and because the sequences of iterates go to x star, it also follows that A times x star is equal to y. Okay. Now, how does that work? It's like this. Because x sub n goes to x star, it also follows that A sub xn also converges to A sub x star. In fact, from this one, this is also equivalent to saying that A sub xn converges to y. And by uniqueness of limit, this simply implies that their limits are equal. So therefore, Ax star equals y. That means the limit of the sequence of iterates is actually a solution of the linear equation. Now, to show that x star is indeed the minimum norm solution, we follow this argument right here. Now, from the definition of the Landweber iteration, it follows that x sub n is in the range of A star, and from linear algebra, the range of A star is contained on the orthogonal complements of the null space of A. Now, we know also from the linear algebra that the orthogonal complement is closed. Therefore, the limit of x sub n is also in this orthogonal complement. And we know from our assumption from the previous lecture, we know that x dagger is the minimum solution contained in the null space, or the orthogonal complement of the null space of I. Now, because this is unique, the unique solution with the minimum norm, and then there is this another solution here also in that same space, then what must follow is that this x star must be that minimum norm solution. Or in other words, the sequence of iterates must converge to the minimum norm solution. And that actually proves the convergence on the exact data case. So that's actually, I would say, 1/3 of the entire convergence analysis that we have to do over here. Okay. Okay. And also, regarding the slides, you should be able to access the slides over there. As long as you have the link, just click it right away, and you must be able to download it. I made sure that the access is for those with the link, which is also in the chat box. Let me just post again the slides. So it's here, there. Okay. In case you missed it, it's over there. Okay. Okay. So now what's left to do is the convergence of the method where you have a noisy data. So same as in Tikhonov regularization, we need to fine-tune the regularization parameter accordingly. And also, as we mentioned earlier, the number of iterations now play the role of the regularization parameter. So therefore, we use again a version of the discrepancy principle, where we terminate the iteration at iteration n sub delta, where the residual at that iteration number is less than equal a multiple of the noise for the first time. Okay? So that means, so you run the Landweber iteration at every iteration. So at every iteration, you check the residual. If it's less than equal to tau times tau delta, you stop, and then you take the iteration, the solution at that iteration as your approximate solution. Otherwise, you keep on iterating. Okay? And to prove that also follows the same procedures as what we did in the Tikhonov regularization. First, we prove some stability estimates as stated in this following lemma. So first, we, as usual, with the appropriate step size, we have this following stability estimates, where the first one is in terms of the approximation errors, while this one is in terms of the residual, where you have the noisy data and the exact data. And note, using the discrepancy principle, note that it only requires as usual, it requires the data, or rather the information that we have, which is the noise and the noisy data. And to prove that, to prove this lemma, we can use again the same procedure as what we use. So let's try to see the proof and sketch it as much as possible. So first, in the first steps here, we recall the iterates of the Landweber iteration with noisy data and the one with the exact data. And then we combine them both by subtracting one from the other, so that we'll get into a useful expression. There, okay. So to get us to some useful expression, we can try to do that one. Okay, now how to do that? By subtracting each, then that will lead us to this one. So that's x sub n delta minus x sub n minus eta times a star, and then you get that one actually. You have a of x sub n minus 1 delta minus x sub n minus 1 delta, and then inside multiplied by a star, you have minus y delta plus y. Oops. There. Okay? Now if you look at this one, we can group the terms further in the following way. So how does that work? So it's like this. We can regroup this one by trying to pair this term here. Iterates here, so we'll have something like identity minus eta times a star a. But so that it will be much clearer, we can actually distribute this one. Minus a star there. And then you have minus eta a star there, and then you have plus eta a star times y delta minus y. Okay, then you group the two terms there, so you have one identity minus a times a star a times x sub n plus n delta, and then plus that same term there. Okay, and note, recall that our initial solution for both the exact and the noisy case, it's just the 0 vector. Okay, now let's estimate this one. Okay, and also by an induction argument, we can rewrite this in a very useful term. In fact, let's say if we have x1 delta minus x1, by using this one, this will be equal to I minus eta a star a times x sub o delta minus x sub o, that's 0, plus this one. So you're actually left with this one. And also by also if you want to look at x2, then by using the same estimates here, we have in this one times x1 delta minus x1 eta a star times, and then by using this result here, then we'll get something like I'll just put eta here times a times this one, that's a star plus this one over here, eta times. Now, in order to express it as a sum, I'll do some very mind-blowing trick here, that you can actually write this one as, put some term equal to 1, and that's just yi minus a star a times a star a raised to 0. And it will just be equal, okay? So that means you can write this sum of the two terms here as a single summation. So that's I minus eta a star I raised to j times a star times y delta minus y. So that's from j equals 0 to 1. And in general, by an induction argument, you can also generalize that for a given iteration n, you will have that estimate there, okay? Let me just write it here. Okay, so that's just equal to this one over here. So eta times the sum of I minus eta a star I to j times a star times now if you look at the summation, notice that the sum is all over only the terms with the j, so you can think that the sum is also just here. So the term which is in bracket is sum of self-adjoint operators, and from spectral calculus in the first part, if you recall, if you have something like f of a star a times a star, and that will be equal to a star times f of a times a star. So therefore, we can move this a star here before the summation. So you have eta times a star times the same summation of I minus eta a times a star okay, and then by some argument with spectral calculus, we can also proceed with a more useful inequality over here. But let me just put it there. Now, if you look at this term over here. Now let's try to detail the spectral calculus in this part. Now from from spectral calculus, we have that if K is self-adjoint operator, then we have the norm of K star K times K star is bounded above by the supremum of square root of t times the absolute value of f of t, where t is taken from 0 to the norm of k squared. Now, we can use that one here. So if you look at this sum, actually, we don't really have to transform it like that. So we can just actually use this one, okay? So if we let f of t be equal to this one, so here to write this one, so notice this is like, if you look at the summation here, this is like a polynomial of a sum of polynomials of self-adjoint operators. Okay, so if you let f of t be the polynomials, in this case, that will be just the summation of 1 minus eta t raised to j. Okay, and then so here note that t there corresponds to the term a star a. And then by using this result over here, we can actually see that if you take the norm of this one, the norm of A star times f of A times A star is also equal to the norm of f of A star A times A star. And that one, I think I have to use another term again. Okay, so by following that one, again, if I write again that one, that's f of A star A. And by using that fact from spectral calculus, you can read that in the book by Heinz Engel, as I've mentioned earlier. This is bounded above by the supremum of square root of t times the summation of 1 minus, actually that one over there. I think I wrote it there, yeah. 1 minus eta t raised to j from j equals 0 to n minus 1. Okay? So that means also that because we need to take the norm of the error, then this means that the norm of x sub n delta is also bounded above by this one. So we have eta times this supremum over here times the norm of y delta minus y. Okay? And here t is taken from 0 to the norm of a square. Okay? And now the analysis of this one will actually be a bit more intricate because we need to find the supremum of this one. Okay, so we will do that later. But now let's first try to analyze this one by using the solution that we outlined there. So if we let g sub n of t be that sum over there, n minus 1, and then let's do a trick where I multiply both sides by t. Okay, so we have g sub n of t times t, and I'll use this very mind-blowing fact that t can be written in this way, minus eta. Did I write it there? Didn't. Okay. 1 minus eta times t minus 1 plus 1. Okay. So we have this one. This is equal to 1 over eta times the summation of raised to j nt minus 1 plus 1. And then, by looking at this one, we can compute the sum of that one as like this. So you have 1 over eta times from, what is it again? From finite geometric sums, that's equal to 1 minus eta times t raised to, there are n terms here in the sum, so that's 1 to the n over 1 minus eta times t times, note that's eta there, eta t minus 1 plus 1. And notice that this gets cancelled, okay? And you're left with this one. 1 over eta times 1 minus eta raised to t raised to n. Okay? And now, so by again continuing some manipulations with the polynomials there, it's already halfway, so let's have a 5-minute break.